Sulu Taiwo, and I'm from Pint of Science, Nottingham. I'm here with Professor Mark Fromhold from the School of Physics, and we're here to ask him a couple of questions. So, how did you become interested in science?
It was really when I was at school, when I was doing my A-levels, and I chose to do a syllabus which emphasised quantum physics. So actually, when I was doing my GCSEs, I was quite bored by physics, and I thought it was all about ladders sliding down friction-free walls and so on. And I thought it was useful from the point of view of getting a job, but I didn't really love it. And then I started to see weird things, like objects could behave not like objects, but as waves, and I found that mind-blowing. I still do, actually. And so it was that kind of really bizarre nature of matter and the way things are that hooked me on science. So really it was a great A-level teacher and a really good modern syllabus.
Yeah, I think for a lot of scientists, like the teachers that sort of pave their journey and like what they want to sort of get into. So it's quite interesting to see it in your case as well. So you mentioned quantum physics. So sort of in a couple of sentences, how could you sort of explain that? Because a lot of people sort of know physics as like forces of motion, energy. What is precisely quantum physics?
It's really saying that objects, we're used to dealing with really big objects like cars, buses, that you can see as a thing that moves around. And as things get smaller and their energy drops, they no longer behave like objects that move as particles. They behave like really extended waves. And so their behaviour completely changes. They show wave interference effects. If you get two waves coming together with two peaks combining, you get a massive wave. Peak and a trough combines, you get nothing. And so that totally changes the way objects behave. So in atoms, wave interference gives rise to well-defined energy levels that mean that you have completely discrete jumps of energy, quanta of energy emitted as an electron jumps from one level to another. And that's really practically useful from the point of view of CD players, DVD players. All these things rely on the quantum wave nature of matter, its wave behaviour.
Yeah, it's interesting you touched upon that. So I know you've mentioned CD players, but
Yeah.
what precisely, what relevance does your research have to sort of today's society?
It's everywhere. It's in our pockets, it's in that camera, it's probably in your watch. So all of microchips rely on this wave behaviour. All of solid-state chips, microchips, rely on the fact that you've got waves going through a crystal lattice, and that means that you've got bands of energies where electrons can move and bands where they can't. And it's entirely that mean that transistors work, that integrated circuits work, that in other areas, medical imaging, MRI machines rely on quantum mechanics, the fact that an object can spin, and it can spin in two different orientations, and you can flip those spins with radio waves. So it's just everywhere. And people it's so ubiquitous that people don't realise that it's just all around us. The world works because of it now. Sun shines because of it as well, actually, on a more fundamental level. If it weren't for quantum mechanics, there'd be no sunshine at all, so that would be pretty sad.
So getting away a bit from physics, so if you weren't a scientist, what job do you think you'd be doing right now?
Oh, I'd write folk songs.
Folk songs, interesting.
I wouldn't sing them, because that would be quite an unpleasant experience for everybody, but that's what I would do if I wasn't a scientist. If I could make money at it, I think.
What's the most unexpected thing you've learned along the way in your journey?
I think the most unexpected thing, if you come from a scientific background, is that it's people that really, really matter. It's your relationships with those people, it's how you get on with your students, with your colleagues, with your peers. It's that teams of people work because of those human interactions. So science and doing the science is great, but it's the people working together that's the best bit, and sometimes the most challenging, but usually the most rewarding bit.
It's quite poignant there, yeah. It's all about the people and
absolutely is,
rather than the technology and all the things that you're dealing with.
It's people that are developing that technology, and people behave like people.
Absolutely. Who would you say your favourite sort of scientist, or could be a person who sort of inspired you?
Yeah, there are many. So I started off working as a solid-state physicist, and I worked for a while in a hospital, and then I changed fields and moved into coal atoms, and there was a person called Wolfgang Ketterle who really made the first coal atom condensate, or one of the first coal atom condensates, and he was extraordinarily encouraging from the point of view of a person that worked on microchips, if you like, moving to work on more atomic physics, more cold atom physics. And so he got a Nobel Prize in 2001, he said, feeling stressed that he's got the date wrong, but I think it was 2001, yeah, it was. But despite the fact that he didn't know me from Adam, I contacted him for advice to think about how we could get into this field in Nottingham. His advice was invaluable. He supported an application for a sense that we set up that led to Quantum Technologies Initiative, so he was massively helpful.